Welcome, everyone. Naoki is going to be talking about Coset constructions of W superalgebras of type B. Feel free to start whenever you're ready.
Thank you for introduction and thank you for inviting me here. In fact, usually I could not join the seminar because it's at 1 p.m. in Denver, but it means it's 4 a.m. in Japan, so I usually cannot join. But today, thank you for shifting the starting time, and I'm very happy to talk here. So anyway, today I talk about Coset construction of W superalgebra of type B. So this is joint work with Thomas and Andy. So if you want to see the detail, please see the archive. So first of all, I will very slowly starting about, let's talk about some concepts. So let's B as vertex algebra on general vertex superalgebra, and W as subalgebra. And then I want to denote coset commutant WB. This is element A and commuting with the or action of OPE for BW equals 0 for B is element in W. This is called coset of W in B. So we want to introduce some notation, G as Lie algebra or G as Lie superalgebra, and VKG as affine vertex algebra associated to G at level K, LK as a simple quotient of VKG. And also Vila C denotes Vila sort vertex algebra of central charge C, and Vila subscript C denotes simple quotient of Vila sort vertex C. So most famous coset result is given by Goddard Kent Reeve, now called GKL coset, in 1986. Its statement follows: if K is a non-negative integer and G is SO2, we consider LK SO2 tensor L1 SO2 and consider diagonal action. It's just the action of LK plus 1 SO2. And the coset gives some very nice discrete unitary series of Virasoro vertex algebra. And now central charge can be written in terms of level K. It is 1 minus 6 over K plus 2 times K plus 3. Oh, that's a very nice construction using unitary series because the simple quotient is very abstract construction, but this coset says more. I mean, we can consider, for example, we can construct a module of this unitary series of Virasoro algebra and so on. Anyway, this coset is so useful. But now recently, Tomoyuki and Thomas and Andy generalize this statement. Now I want to say called SEL coset, given by 2019. The statement follows: if K is complex number, satisfying that K plus H check is not a negative, non-positive rational number, and G is ADE type, then they consider BKG tensor L1G and consider also diagonal action taking commutant. Then coset vertex algebra is isomorphic to principal W algebra of G. And now level L is just satisfying that the written in terms of K. L plus H check equal K plus H check over K plus H check plus 1. And G is SO2 case, this becomes Virasoro vertex algebra. And this is a universal statement. But using this universal statement and the character computation implies that simple quotient statement as a corollary of the construction says that G is ADE type, K is now admissible level of G, and then consider simple quotient, I mean LKG tensor L1G, and the coset of LK plus 1G is isomorphic to now simple quotient of principal W algebra of G. And now in this case, L becomes a non-degenerate admissible level. So this becomes now a minimal series of W algebra. So we know that rationality and C2 cofinance due to Tomoyuki's result. Anyway, this is very nice. So the question is why we need to assume that G is ADE type. The answer follows. The answer comes from the ideal proof, and because they use Granker-Kant's construction. So now G is ADE type, and Q is root lattice of G, and now H is Cartan subalgebra of G. This is isomorphic to H star by using the normalized bilinear form. And this is now Q tensor C over G. I want to denote by pi k is just a Heisenberg vertex algebra, associate H star at level k. And then the tensor product of fork module of pi k, I want to denote by pi 1 lambda. It's now level is 1. And the lambda is an element in root lattice. Then the direct sum of pi 1 lambda is I want to denote by VQ as a famous lattice vertex algebra of Q. The point is this has a structure of vertex algebra. And the Frenkel-Katz says that the VQ has a G hat module structure and isomorphic to now L1G. This gives a free visualization of L1G. The action is follows: E alpha, H alpha, F alpha. This is some SL2 triple corresponding to alpha axon, E upper alpha. This is some exponential of alpha. So that's like a lattice element vertex algebra, and just the H alpha goes to alpha Z. This is Heisenberg field. E minus alpha Z is also vertex algebra corresponding highest weight of minus alpha. Anyway, this gives Frenkel-Katz action, this is G hat action, and this gives L1G isomorphic BQ. And HCF says that the coset of diagonal action of VKG tensor L1G is contained, embedded in Heisenberg coset of pi k plus H check tensor BQ. I mean, the Heisenberg coset means that of this pi k tensor lattice vertex algebra is now, it becomes also Heisenberg. And also this means that they say that first of all, a coset has nice free visualization. And also they say that image of embedding characterized by kernel of screening operator. I mean the kernel of SI. So SI, some operator comes from some exponential minus alpha I over L plus H check Z, and they take some zeros vertex operator and then consider kernel, and they say this isomorphic to image. And also due to theorem of W algebra, this kernel of screening operator is isomorphic to principal W algebra. So this implies that SEL isomorphism, and we obtain the result. That's the reason why G is assumed that ADE type. So the natural question is, what is DB type? For example, this is today's talk. So now point is now we cannot use VQ, but now we want to use, instead of VQ, we want to use F2n plus 1. This is 2n plus 1 free fermion vertex super algebra. So this is even part, looks like affine SO2n plus 1 hat module is just L10, and the odd part looks like L1 pi 1. This is fundamental rate or corresponding to alpha 1 of SO2n plus 1. This is phenotype representation that our theorem state follows. This is due to Thomas and also Thomas and Andy gives the same different group, but anyway. So if K plus H check of B is not a non-positive rational number, then coset of VK of type Bn tensor F2n plus 1, and consider coset of diagonal action, then this isomorphic to principal W algebra of type B, but not just the type B, but type super B type. I mean principal W algebra of OSP 1 to n. And also L and K relate similar formula as 2 times of L plus H check of OSP equal K plus H check B over K plus H check B plus 1. Now H check B is equal to 2n minus 1, H check OSP equal n plus half. The reason why OSP 1 to n is called super B type is just a Dinkin diagram is very close to B type. So you see a Dinkin diagram looks like alpha 1, alpha 2, alpha n minus 1 is same as B type, but alpha n is just odd. Just odd root. This means that the root vector is just odd space. And point is this contains even part. This even part is just SP to n. The even part looks like alpha 1 to alpha n minus 1 the same, but the long root just corresponding to 2 alpha n. So I want to write so this alpha n is just a short root in OSP 1 to n, and this 2 alpha n is long root, and the other one is just a middle one. the structure of OSP1 looks like this anyway. This is OSP1, and this is a mixture of B type and C. Anyway, this is statement. So why this is so interesting is because, for example, if n equal 1 case, principal W algebra OSP12 is just n equal 1 superconformal algebra, vertex superalgebra. And in general case called Fatih-Lucan of the WBN algebra, very classical family as a generalization of n equal 1 superconformal algebra. So anyway, very famous series and natural generalization. So very interesting. And I want to comment one more point, and just the duality. So if G is the algebra case, and then we want to say LG is Lagrange dual G, then we have isomorphism between principal W algebra of level K and level L of the principal W algebra of LG. Then our K and L relate some formula that we have nice isomorphism. And K plus H check times L plus LH check equal 1 by times R check. R check is racing number, this is 1, 2, 3, but LH check is Xerox number. The point is OS principal W algebra of OSP1 satisfies very similar relation. So point is that so now I want to this statement also proved by myself. The statement is principal W algebra of OSP1 to N is isomorphic to principal W algebra of OSP1 to N, but level K and L is related by similar formula. 4 times K plus H check times L plus H check equal 1. So what the point is that the Lagrange dual means that changing root and root. So in this case, changing root and root means just changing short root and long root in thinking diagram of SP1 to N and SP2N, and the middle root is same. This means that we can define Lagrange dual OSP1 to N, and then the Lagrange dual OSP1 to N is just itself, because changing just short and long root. So that's the reason. Anyway, we can consider such a similar result and obtain this result using the different also screening operator. But anyway, very fast. Is there any question? Not? Okay. I have one comment on our statement or theorem. A theorem is essentially same. And so we also consider using the same technique of SEL, we also consider free visualization of Coset. Also, our Coset is embedded in Heisenberg Coset of Heisenberg tensor sum fermionic vertex algebra, and then image can be characterized by screening operator, and we observe that screening operator is isomorphic to principal W algebra of OSP1. Everything is same, so just nice generalization of SEL Coset. Okay.
Oh, can I ask one question?
Okay.
So in general, so screening operators just might be bigger than the image of W algebras. How can you how to say remedy this difference for these levels?
What do you mean bigger?
So the image of the Euler map of W algebras and the joint kernel of screening operators are the same only if
you want to consider about the level K?
Yeah.
Yes, in fact, the statement I skipped the statement precisely, but essentially isomorphism between kernel screening and W algebra by assume that K is generic. Because if K is non-generic, then the kernel screening are also bigger than W algebra. The point is that first of all, we prove everything for generic level, but non-generic level, we consider about the character formula. The point is the character between the two Coset and the character of W algebra. We essentially same assume under this level condition using the some property of characteristic category. Essentially same argument used in ACS paper. I also applied the same argument because essentially our module is not OSP, just a type B type affine. So we also apply same technique and obtain the same isomorphism. The point is we prove that everything is generic level, and then we consider about the more general level under this condition.
Okay, thanks.
Okay. Other question? If not, I will continue. Okay, thank you for question. So now we want to consider about applications to representation theory. So now, we want to write the note by P plus. This is a dominant integral weight. And now lambda is now dominant integral weight of type B. And then we consider VK lambda. This is a Y module induced from the finite dimensional simple finite dimensional representation of Bn at the highest weight lambda. So we tensor VK lambda tensor F2n plus 1. And we consider about the diagonal action module. Each module becomes just like VK plus 1 mu if K is generic. And then the multiplicity space is just looks like this. And the multiplicity, our theorem says multiplicity space is just a module of principal W algebra of OSP1 to F. I want to write WL OSP lambda mu. So now we want to consider CDO as the CDO is what is just this means that we consider algebraic group G, and Lie G is just our Lie algebra G. And then we consider arc space or infinite jet scheme of G, and consider coordinate ring on this jet scheme. The point is this jet scheme coordinate ring has naturally a GT module, and also can extend GT plus CK module, and now central element K acts on level K. Then we consider induced module as this we want to call CDO. And then this has a VKG module structure. And point is this K plus L satisfying that K plus L equal minus 2H check. This has more additional structure. This means VKG tensor VLG module. And if K is errand generic, this has nice decomposition. This means that VK lambda tensor VL some lambda star. Lambda star is a Y group action of lambda by longest element in Y group. And this decomposition is induced from the classical Peter-Weyl theorem of regular representation. The point is that just this CDO has a very subtle structure, and satisfying that it's nice. This decomposition under the K generic. So now we introduce equivariant W algebra. This is just a Drinfeld-Sokolov reduction of CDO for first component factor. So this means I want to write WKG, this Drinfeld-Sokolov reduction of CDO for first factor. First factor means this decomposition looks direct sum of Drinfeld-Sokolov reduction of BK lambda tensor BL lambda. I mean, right second factor tensor component is just the same, that the first component looks like Drinfeld-Sokolov reduction. Anyway, this is equivalent W algebra. Because if you consider associated variety of this vertex algebra becomes equivariant Slotway slice, introduce the Rousseff. And if you consider the algebra of this equivalent W algebra becomes the equivariant finite W algebra into the Rousseff, that's called this is called the equivariant W algebra. Anyway. So we consider G as SP2 n type, I mean Cn type. We consider equivalent W algebra type Cn tensor F2n plus 1. So this equivalent W algebra part becomes this direct sum plus Drinfeld-Sokolov tensor BCL something. Anyway, F2n. And now we want to write the Feigin-Frankel duality. This first component is a module of principal W algebra of type C, but Feigin-Frankel duality says type C W algebra is isomorphic type B, so we want to change this C to B. And the weighted lambda is changed by lambda tilde, but we have such a isomorphism. The second and third term is just changing the position. It is nothing to that. So that point is that next this technical statement, they mean that the Arakawa-Krutich Feigin show that tensoring, this is now retensoring integrable representation. So tensoring integral representation and taking Greenfield circle reduction is commutes. This is a statement, very non-trivial statement that the point is they changed the Virasoro element technically that they obtained such a state. So we obtained the now we changed the range of Greenfield circle reduction. Now first one is the Greenfield circle reaction of B lambda tilde, that this isomorphic to Greenfield circle reduction of B lambda tilde tensor F to n plus 1. This is very non-trivial that we obtain such isomorphism. But now this part, this appearing in our theorem. So we have isomorphism using our theorem says this decomposed to some module. We decompose module of direct action. This is a module of B type of level K prime plus 1. And now after this, we taking Greenfield circle reduction for this diagonal action. So this part is just Greenfield circle reduction of level K prime plus 1. And appearing in the multiplicity part is just we set module of principal W algebra OSP 1 to n. And the remaining part is just affine of type C. So this is, so point is we can find that this decomposition contained module structure of OSP 1 to n, principal W algebra. So this means we can take in coset of principal W algebra OSP 1 to n inside equivalent W algebra tensor F to n plus 1. And our theorem says that if K is generic, this coset is isomorphic to affine vertex algebra of OSP 1 to n. The proof is very technical. So at least we can find in weight one space. This weight one space we can find OSP 1 to n, right? But the remaining part is we compute character. So character says that the other part is generated by weight one space. And we know that weight one space is OSP 1 to n, so we have some isomorphism, at least K generic level, but anyway, this gives a proof. And the point is just this decomposition says more. I mean, if you remove this OSP part, remaining part is some module. This is module of W B type or just W C type, WC module. And this is affine SP to N module, right? So this means that now affine OSP 1 to n module of highest weight mu is equal to decomposed to SP to n, and the multiplicity space is principal W algebra type C. This is some consequence of our decomposition, but at least using our theorem too, we obtained such a module decomposition. Everything is so technical that we obtained such a result. So our theorem 3 says, that if K is admissible level for type Cn, then we consider simple quotient of affine OSP 1 to n. Then first of all, this is LK SP to n tensoring simple quotient of W algebra of SP to n module structure, and K and L related by this formula. Oh, this is a nice result. I mean, because we have universal statement, so we obtained the admission level statement. And the second statement of the PRK is the set of admission rate as level K. And then this is the condition set lambda is now P plus and the satisfying some condition. Then mu is an element in PRK intersect Q. Then module of affine OSP 1 to n can be decomposed to SP module and the principal W algebra module. Then LK OSP mu is now decomposed to direct sum of LK SP lambda tensoring WL SP lambda mu. And now WL SP lambda mu is just a Greenfield circle reduction of something LL SP lambda. This is just a spectral flow. corresponding to mu. This is just shifting the action of shifting the action by corresponding to the Heisenberg action by twisting mu. Anyway, we can identify this multiplicity space as this one. And the third statement is this: if you collect all LK OSP mu, this gives a complete list of simple ordinary LK OSP 1 to n modules after isomorphism. And the last statement is the category of ordinary affine OSP 1 to n module is semi-simple relations. So now fusion. And this is very good. This is our theorem. The point is last statement is known by Gorik-Sirganova for semi-simplicity, but we obtained rigidity. And also, we obtained the corollary. Corollary says the category of ordinary LK SP2N module is semi-simple rigid. So this is fusion. So, so the question is how to prove this statement. Everything is so non-trivial. So I should explain something more. So first of all, we need to show that at the mystery level of this module. This is some technical computation, but so let's remember this decomposition. Let's remember this decomposition. So universal case, we have this module decomposition, at least mu equals 0. We have nice extension theory. It means that affine OSP is extension of affine SP tensor, principal W algebra of type C. So this means that we can apply extension theory. So extension theory means follows. So if V is vertex algebra or vertex superalgebra, then if satisfied, for example, if V is C2 cofiniteness, we have nice category of vertex algebra module. If you consider, for example, if you consider the category of generalized vertex algebra module, then the category has a structure of vertex tensor category. This means that the module category has nice fusion product induced from PZ tensor and satisfying nice associativity and so on. But anyway, you have braided tensor category structure, and at least the super case also braided and linear abelian structure category. But anyway, in that case, if you consider extension of vertex algebra, the extension becomes algebraic object in the category, and we consider about the induction function. Originally consider about Kirchhoff-Ostrig, but now von Kirchhoff-Lepofsky consider removing rigidity and define induction function. And Thomas, Schank, and Robert generalized super cases, but they said more what it means. So Thomas, Robert, consider about extension theory. It means that if B, W, and A as a vertex superalgebra, and also B tensor W is subalgebra A, and then also A has nice decomposition as a module B tensor W, and the decomposition looks like X tensor some tau X, and we assume that X is in equivariant simple module, and I removed that, but in fact assume that tau X is in equivariant W module. And if you know that, in this case, and they said gluing, and in that case, we have a nice relationship between the A module and the B module tensors W module. And for example, if you know that the module category of B is semi-simple, then this CV is braid reverse equivalent of, and this is tau CV, this is some generated, this is a W module category generated by tau X, and then this CV is also, we know that rigid. So this, at least this implies that we apply our setting. This A is a affine OSP 1 to n, and now B is a principal W algebra of type C, and tau X is a module category of affine SP to n. Then we compute nicely. For at least we need to compute this competition. At least we need to consider this. what is appearing in the decomposition, that we can compute this, and then after computing this statement, we obtain everything. For example, we obtain semi-simplicity and rigidity in the category. This is our argument, and then we obtained this statement as a corollary of 7. Oh, very quick, but any other question? Everyone knows so well? Okay. Oh, this is very quick. Sorry, I don't think so much so quickly, but okay.
Can I ask one thing?
Okay.
Maybe I missed something. What is your original input for the rigidity? So for example, SP2N has a certain rigidity.
Principal W algebra of type C.
Okay. So
yeah.
rational C is a cofinite case?
Yes, in this case, that's true. That's the reason why we have rigidity, because Tomoyuki gives the duality functor in the category, and we obtain the rigidity, so we obtain.
Okay, thank you.
Or just say Robert's theorem says this B category is rigid, so we obtain. I mean, semi-simplicity implies, and decomposition, the existence of algebra structure implies rigidity. Okay. So I don't prepare so much. I'm sorry. I want to explain some future works. So first of all, I also want to continue the generalization of SEA paper. So we have two technical problems. One is a vanishing cohomology theorem. What is vanishing cohomology theorem? So Tomoyuki have a nice theorem about vanishing cohomology or Greenfield-Sokolov function. The statement follows: if G is simply algebra, then they consider category O of affine G hat, affine G at level K but non-critical level. Then we have decomposition using the affine extended Y group action. But anyway, we have such a decomposition. Then if you take some object in N in this some block of the category O, the statement is lambda satisfies nice condition. Greenfield-Sokolov functor is 0 if the I is non-zero. I mean, vanishing of cohomology theorem satisfied. This is very important because the Greenfield-Sokolov functor is exact functor. This means that if you study something, some standard object in the category O, and if you know that the simple object, we obtain everything because exact. So this means that we at least we have a multiplicity formula or true, and this means we can compute the character formula and so on. Anyway, very useful. The other important work is just the Z algebra or principal W algebra. In fact, it is just the center of universal enveloping algebra. So this is very nice. So using these two techniques, SEA paper says that if K is at the admission level, LK mu tensor L1 mu has nice decomposition. And the multiplicity space is just a TL lambda mu. It's just also Greenfield-Sokolov reduction of spectral for motion. So I want to generalize this statement for Bn type. So to know that what we should say, we at least we need to know that no. Sorry. At least we know that to generalize this theorem. Oh, I should say voice. So at least to study and to generalize our theorem, we need to know that the representation theory of principal W algebra of OSP1 to N, right? So this means that we need a vanishing cohomology theorem of G is OSP1 to N. This means we need to study category O of affine OSP1 to N. And essentially, my idea is just also vanishing cohomology theorem follows for all still hollows for OSP1 to N case. This is just one of recent work. The main difficulty is Tomoyuki uses some very classical result of Arkhipov. Arkhipov has nice some freeness result. Some freeness of freeness gives some vanishing of cohomology. So this is very technically important, but we need to study OSP1 to N case. So that is one of technical difficulty, but I think we can do the same result using the same technique of Arkhipov. That is one of difficulty. The other is algebra. We need to study the algebra or principal W algebra of OSP1 to N, right? Just because this result is true for G's real algebra case, which we now study the G is OSP1 to N. But now, principal W algebra of OSP1 to N is half integer graded. So this means that we can define two kinds of the algebra. One is just a non-twisted, just usual the algebra. The other is twisted algebra. So twisted algebra means that the representation of twisted algebra is simple module is corresponding to twisted module of vertex algebra. In this case, for twisted module means the twisted module corresponding to automorphism for canonical automorphism defined by odd part is just -1. This is some standard canonical automorphism that and Desor and Katz compute the twisted algebra is just a finite W algebra of OSP1 to N. And the problem is what is non-twisted algebra? Non-twisted algebra is not known, but I think that the non-twisted algebra or principal W algebra of OSP1 to N is also isomorphic to center of universal enveloping algebra of OSP1 to N. And that is even part of finite W algebra of OSP1 to N. So using these two statements implies that at least if you know that's algebra, we have nice classification of simple module. In this case, just a center means that the simple module is classified by central character. So anyway, using two results, we apply our setting and obtain generalization of ACL statement, and then we can also want to study a category of module or principal W algebra or OSP1 to N, and combining these results, we can study some mixture of principal W algebra or OSP1 to N, principal W algebra of type B type or type C type, and apply alpha in cases anyway. Okay, I'm sorry, that's very quick, but
This is great. Thank you so much, Naoki. Let's thank Naoki and stop the recording so we can move on to questions.